Welcome to the MOOCs course Mechanical Unit Operations. This is about fluidization. The title of this lecture is Fluidization Part 2. It is a continuation part of the previous lecture fluidization what we have discussed. So, before going into the additional details about the fluidization, we will have just a recapitulation of what we have seen in a previous lecture on fluidization. So, types of fluidization we have seen different types of fluidization pattern are possible depending on the type of fluidizing medium. That is, if the fluidizing medium is a liquid, then different patterns are possible in general, and then if the fluidizing medium is a gas, then different flow patterns are possible within the fluidized bed in general. Okay. That also depends on the density difference and then velocity, etc., and all those things. So, we have seen, but the fluidization characteristics or fluidization patterns in general may remain same up to certain extent irrespective of whether the fluidizing medium is a kind of gas or liquid. Okay. So, that is what we have seen. So, have a kind of recapitulation. Let us say you have a bed packed with kind of particles are shown here. Right. So, this is a kind of bed which is packed with a kind of particle. We have a kind of column, and then part of this column is packed with a few particles. At the bottom there is a kind of perforation plate, so that particle should not fall down, and then from bottom gas or liquid is flowing upward motion like this. Okay. But if the velocity is low, if the fluidizing medium velocity is low, whether the fluidizing medium is gas or liquid, that is not going to affect the packing structure of the bed. So, if the velocity is as low as possible, so that the packing structure of the bed is not being disturbed because of upcoming fluid, that is upcoming fluidizing medium, then we can say such kind of situations are fixed bed conditions. Though at the top it is not constrained, the bed is not constrained at the top, but however the velocity of the upcoming fluidizing medium is low, then packing structure is not changing much. So, it is remaining as a kind of similar situation as in a kind of fixed bed. Right. So, under such low velocities we can use Ergun equations without any difficulty, even if it is not packed at the top, or even if the bed is not constrained at the top. Okay. So, this is anyway free board area that we have already seen. So, free board area would be available anyway for the particles to move on if at all if they are moving up. So, but subsequently if you gradually increase the velocity, right. So, that means the arrow direction is increasing velocity we have shown here. So, that means from one picture to the other picture as we are moving, the superficial velocity of the fluidizing medium is gradually increasing. So, if we go to low to moderate velocities, so then what happens, the packing structure of the bed may be slightly being disturbed, and then that becomes slightly looser and then start expanding, and then this behavior can obtain by using both gas or liquid type of fluidizing medium. Any fluidizing medium you can use it. So, this condition we call it minimum fluidization, under which the total resistance offered by the particle is balanced by the buoyant weight of the bed. Okay. So, that is the balance under that condition, or like when the particles are moving, expanding or going away from each other slightly. So, there will be a point, the point corresponding to certain velocity, there will be a velocity corresponding to which the overall resistance offered by the particle for flow of this fluid is balanced by the buoyant weight of the bed. So, that condition we call it as incipient fluidization point or minimum fluidization point, and then corresponding equations we can get by replacing delta P is equals to Fg minus Fb divided by cross section area of the bed. Okay. So, this is the balance. So, after this point onwards, once the velocity reaches certain point, certain velocity at which the minimum fluidization started. So, from that point onwards, even if you increase the superficial velocity of the fluidizing medium, the pressure drop is going to remain constant. It is not going to change. That is what also we have already seen. So, that is the reason at minimum fluidization point pressure drop we are equating by Fg minus Fb by cross section area S naught. From there we get delta P by L is equals to G delta rho P 1 minus epsilon, and then epsilon should be replaced by epsilon m, that is the maximum fluidation if the bed is under a fixed bed condition, and then from that point expansion of the bed takes place. So, that is the minimum fluidation if the bed with respect to the fluidation conditions if you take. So, after this point further increasing the velocity, the expansion of the bed is going to take place and then voidage is going to increase, and then bed will no longer be in fixed bed conditions. Okay. So, further if you increase the velocity, then the effect of type of fluidizing medium is going to show in the patterns that are going to form. So, let us say if you have a the fluidizing medium is a liquid, then further increasing the velocity, superficial velocity of the liquid fluidizing medium, the bed uniformly expands. So, you can say a kind of uniform expansion is there, so that at any point within the bed if you take, or at any cross section within the bed if you take, the bed density is going to be same, or it is going to be remain almost constant. That is the whatever at any cross section at any position within the expanded bed, the volume fraction of the particles and then volume fraction of the fluidizing medium or void space is going to be remain almost constant. So, that we call as a kind of particulate fluidation or smooth fluidation. However, if your fluidizing medium is a gas, then as the velocity increases, there will be a kind of situation where the bubbles may be forming, voids or bubbles may be forming, which are almost free of particle. There may be 1 or 2 particles, but in general these voids are free of particles, and then you can see those bubbles are moving up rather fast compared to the bed. You can see if you compare with the minimum fluidization conditions, the most of the particles are they are not raising up much larger height compared to the minimum fluidization condition. So, you can see only the bubbles are raising more, only there are a few particles beyond this point also. What does it mean by bubbling fluidization condition, which is obtained by the gas flow rate? So, if you increase the velocity, most of the velocity most of the gas that is going to form a kind of voids or bubbles, and they are moving quite rapidly, or the expansion of the bed whatever is taking place, that is primarily taking place because of the expansion or the raising of the bubbles or the voids, or otherwise the dense phase or the particulate phase is almost like under the similar conditions as in a kind of similar height as in a kind of minimum fluidization conditions. That is what one can say from here. Okay. And then further, the bed density at any location within the bed if you take, it is not going to be same, it is going to be different from one location to the other location. Then further, if you have a kind of increasing the velocity, and then fluidizing medium is a kind of gas, now you make the channel or the column in which you have done the packing of the material bit narrower, then these bubbles whatever are forming by the bubbling fluidization, they increase in the size, and then the kind of slugs may be forming out, which may be eventually occupying most of the cross section of the bed. This can happen at high velocity for gas fluidizing medium, but the channel has to have a kind of a smaller dimension constraint, or the a narrow channel compared to the other cases like bubbling fluidized bed. Then we can have these slugs. So, these slugs can be axial slugs as shown here, or they can be almost like kind of flat slugs as shown in the subsequent figure. Then further, if you increase the superficial velocity of the fluidizing medium gas, then the particulate phase and then the bubbles whatever are forming, they will be under a kind of turbulent conditions, and turbulent fluidization will take place. Under such conditions, particles may even go out of the bed. However, those particles in general collected and then sent back to the column again. Okay. So, if we are recirculating like this, then that bed is known as the circulating fluidized bed. But at large velocities, at very high velocities compared to the minimum superficial velocity, whether you are using a gas or liquid as a fluidizing medium, a kind of a pneumatic transport will take place where the particles are farly apart from each other, and then they may be going out of the bed, and then a kind of transport is occurring. So, these are the types of fluidization in general we have seen, and they are general observation. They may not necessarily be always be forming always. Let us suppose whatever the pneumatic fluidization that you see in case of liquids, if the delta rho, if the density difference between the particle density and then fluid density is a kind of very small, then a kind of some kind of bubbles may form even when you use a kind of liquid as a kind of fluidizing medium. On the other hand, if your fluidizing medium, even if it is gas, but the density difference is kind of very large, that is rho p minus rho, the density difference between particle and then fluid densities is kind of very large, then even using this gas phase as a kind of fluidizing medium, you may expect some amount of particulate fluidization. So, it depends on these properties. Other properties are also depend, sometimes particle structure, nature of the particles, they are all going to have effect in the flow patterns in general, but generally we can experience this kind of behavior. Depending on the particle size, type of the particle, there are different types of particle sizes depending on the size of the particle as well as the density difference between the particle and fluidizing medium. So, the particles are categorized as A, B, C and D type particles, and then you can have a kind of mixed behavior also possible in general. Okay. Further, what we have seen in the previous class, we have developed expressions for the minimum fluidization conditions, or the equations we have developed for the minimum fluidization conditions, and then from those equations we can evaluate what is the velocity required, minimum velocity so that to incur a kind of a fluidization within the bed. So, that velocity calculations we have done. So, how we have done? So, we have taken a kind of a Ergun equation. In the Ergun equation, left hand side whatever delta p by L is there, that is replaced by G delta rho 1 minus epsilon m, where epsilon m is the minimum voidage at minimum fluidization condition or maximum voidage possible for a bed to be behaving as a kind of fixed bed condition. Either way we can say, or it is a kind of a cutoff between fluidized bed and then packed bed. So, at that cutoff whatever the voidage is there, that is epsilon m, and then corresponding velocity is known as the minimum fluidization velocity, that we replaced by VO m bar, that is VO bar is replaced by VO m bar. So, that that is what we have done Ergun equation, right. So, in the Ergun equation, left hand side whatever delta p by L was there, that we replaced by G delta rho multiplied by 1 minus epsilon m, and then right hand side terms wherever VO bar was there, that was replaced by VO m bar. So, there was here 1 minus epsilon m whole square, and then here 1 minus epsilon m was there. So, that 1 minus epsilon 1 part can be cancelled out in the left hand side whatever is possible. So, the final equation that we got this one. So, this equation can be used for the entire range of Reynolds number. Let us say if you know the packed bed Reynolds number, or the Reynolds number in the packed bed when a fluid is flowing through a bed, that REP if you know, then different equations we can use if REP is less than 1 and then REP is greater than 10 power 3. If REP is less than 1, only this term is going to be important, and this term can be, second term can be neglected, because that is because of the convection. If REP is greater than 10 power 3, this first term can be cancelled out in the right hand side term, and then we can have only the second term in the right hand side, because we need only convection part. So, we know that in the right hand side first part, first term is indicating about the viscous losses, and then second part indicating about the kinetic losses. So, viscous losses are predominant at small Reynolds number, kinetic losses are predominant at large Reynolds numbers. So, in order to have simplification and mathematical equations to develop for REP less than 1, we have taken left hand side is equals to first term of the right hand side, and then we simplified. So, then we got this equation. Similarly, if REP is greater than 10 power 3, then left hand side we keep as it is. In the right hand side, we have taken only this second term and then simplified that equation for minimum fluidization velocity, that we got this equation. So, if you know the Reynolds number for packed bed condition, then if it is less than 1, this equation you can use for a minimum fluidization to occur. or to calculate the velocity for so that minimum fluidation to occur. And then if you know that Reynolds number for packed bed conditions, it is greater than 10 power 3, then you can use this third equation, so that to get the what is the minimum fluidation velocity, so that fluidation start occurring or bed expansion start occurring. So, if you do not know Reynolds number, this entire equation you have to use. You substitute the fluid properties and then geometry and then particle characteristics here, and then simplify this equation. You will get quadratic equation for VO m bar. If you solve that equation, you get a minimum fluidation velocity. Minimum fluidation velocity can also be calculated in terms of Galileo and Reynolds number. For that, what we have done, whatever the equation, that previous equation number 1 is there, that equation both sides we multiplied by rho dp cube by mu square epsilon m cube by 1 minus epsilon square. Then we right hand side terms we simplified, left hand side terms we kept as it is. Right hand side terms when we simplified, we got here 150 multiplied by RE for packed bed plus 1.75 multiplied by RE square for packed bed, but this RE is at minimum fluidation condition. So, VO m bar and then epsilon m are used here. Okay. So, this equation for spherical particle, if you write, Galileo number is equals to 150 REM plus 1.75 REM square. REM I am using because this Reynolds number at minimum fluidation condition, or the corresponding velocity that has been used to get this Reynolds number is the minimum fluidation velocity, where this left hand side term of this equation is known as the Galileo number, and then REM, as I already told, it is the Reynolds number for packed and fluidized bed conditions, but at minimum fluidation conditions. Further, we have seen Galileo number. This is quite similar to our K factor. K factor what we had in our single particle settling conditions, K is equals to dp cube root of g rho delta rho by mu square, that is what we have seen. So, that K cube would be dp cube g rho delta rho by mu square. So, that g delta rho dp cube by mu square term is also there, and then there is a additional correction for a kind of packed and fluidized bed conditions. So, is there any connection between this that one has to find out? Okay. Anyway, but this actually here K we have found, in case of single particle, if it is less than 2.6, then we say it is a Stokes regime, and then corresponding free settling velocity we have used. If it is greater than 68.9 or between 68.9 and 2300, then we say that the settling velocity is under Newton's flow regime, and corresponding velocity equation we have used. But in the case of packed and fluidized beds, there is no such kind of sharp transition from one flow pattern to the other flow pattern. So, we cannot have this less than this Reynolds number is a kind of laminar flow. So, some people say REP less than 1 is going to be a kind of laminar flow for packed bed, but even some researchers argue that up to REP 5 to 10 also the bed remains as a kind of laminar flow conditions. So, those kind of ambiguities are there. So, that is the reason corresponding limit numbers for Galileo number we cannot have for these conditions, though by mathematical appearance this K and G are appearing kind of similar way. Okay. So, now we take problems. This is what what we have studied in a previous class about the fluidization, a summary. Now, we take a problem, example problem. A bed consists of uniform spherical particles of diameter 3 mm and density 4200 kg per meter cube. What will be the minimum fluidizing velocity in a liquid of viscosity 3 millinewton second per meter square, that is 3 millipascal second. So, that is 3 into 10 power minus 3 pascal second, and density is 1100 kg per meter cube. Assume voidage at minimum fluidization conditions as 0.4. Then calculate what is the minimum fluidization velocity, that is the question. So, particle size is given, its density is given, epsilon m is also given, then fluid viscosity, fluid density are also given. So, we can calculate Galileo number, right. Galileo number here G rho dp cube delta rho by mu square multiplied by epsilon cube by 1 minus epsilon square. If you substitute all these terms here, this is G, this is rho, this is dP cube, and then this is rho P, this is rho, this is mu square, and then this is epsilon m cube, and then this is 1 minus epsilon square, 1 minus epsilon m whole square. So, then if you substitute all these values and then simplify G, a Galileo number, you will be getting as 17841.12. Now, this one you substitute in this equation that we have derived. Galileo number is equals to 150 REM plus 1.75 REM square, and then you simplify this equation further and then solve this equation to get the roots of this Reynolds number, so that you get REM. One positive, one negative value you will get. Negative value is not having any meaning here. So, we take positive value as the answer. So, that comes out to be 66.8319. So, now REM we know as rho dP VO m bar by mu 1 minus epsilon m. So, that you use it here. So, REM we know dP rho VO m bar by mu 1 minus epsilon m for packed and fluidized bed. So, here this you equate to 66.8319. So, in this equation dP is known, Re is known, mu is known, epsilon m is known. So, you can calculate VO m bar. It comes out to be 0.03645 meter per second or 36.45 millimeter per seconds. So, that is the minimum fluidation velocity. We will take another problem. A similar problem, but now we directly use the equation to get the minimum fluidation velocity rather doing the Galileo number calculations. So, consider a column packed with spherical beads diameter 1.1 mm having density 1240 kg per meter cube. Fluidizing medium is water with density and viscosity as given as 1000 kg per meter cube and 0.01 poise respectively. Viscosity is given in poise. Okay. So, what is the minimum fluidation velocity with epsilon m being 0.4? Exactly the similar problem what we have done previously, but other way we calculate. So, this is the equation minimum at minimum fluidation condition. This is the equation 150 mu VO m bar 1 minus epsilon m divided by pi s square dP square epsilon m cube plus 1.75 rho VO m bar square pi s dP epsilon m cube is equals to G rho P minus rho. Here except VO m bar everything is known. We can substitute all these quantities and then for a change we do this one in CGS unit. Okay. So, when you substitute all these numbers here, we can get the equation for minimum fluidation velocity. By solving that equation, we can get the minimum fluidation velocity. So, 150 here, this is constant, viscosity is 0.01 poise, VO m bar is not known, 1 minus 0.4 is 0.6, pi s square is 1 because it is spherical beads, dP is 1.1 mm, so 0.11 centimeter square, and then epsilon m is 0.4 plus 1.75, rho is 1000 kg per meter cube, so 1 gram per cc, VO m bar square do not know, divided by pi s is 1, dP is 1.1 mm, so 0.11 centimeter, and then m cube is 0.4 cube is equals to G is 980, and then rho P minus rho is 1.24 minus 1, so that is 0.24. Okay. So, when you simplify you get this equation, and then when you solve for VO m bar you will get 0.194 centimeter per second because we have solved it in CGS units. Okay. So, corresponding Reynolds number at minimum fluidation velocity, if you calculate, it comes out to be 4.41, which is slightly beyond the laminar flow region. Another example, an oil of density 900 kg per meter cube and viscosity 3 milli-Newton second per meter square is passed vertically upwards through a bed of catalyst consisting of approximately spherical particles of diameter 0.1 mm and density 2600 kg per meter cube. At approximately what mass rate of flow per unit area of bed will fluidation and transport of particles occur? So, it is not asking the minimum fluidation velocity, corresponding mass rate it is asking per unit cross section area, that is in kg per meter square second. So, that is rho into VOM bar we have to calculate. And then transport of particles in general that occurs at the free settling velocity of the particle. So, for those particles free settling velocity we have to find out. Assume voidage at incipient fluidation is 0.48, epsilon m is given 0.48. So, fluid properties are given, particle properties are given, bed voidage is given. So, at what mass rate of flow per unit area of bed fluidation will occur. So, that is density multiplied by minimum fluidation velocity, that we have to calculate, that we call it as a mass velocity or G. So, whatever this equation is there here. So, this equation you multiply by rho and divide by rho in the right hand side. So, rho VOM bar you can write it as G. So, this one. So, in terms of G you can write this equation like this. So, here also now except G everything is known. So, you substitute all the values. So, then you get this equation. When you solve this equation you get G is equals to 0.071 kg per meter square second. Now, similarly transport of particles occur when velocity is equal to terminal velocity of particles. So, we have to find out the terminal velocity of particles, but which equation should we use? We use the equation corresponding to Stokes' regime or corresponding to Newton's regime? We do not know. So, first we have to find out that. How we find out? We have to find out k value, as we have seen one of the previous chapters. So, k is dp cube root of g rho delta rho by mu square. So, you substitute all these values here, then you will get k value 1.186, which is less than 2.6. That means it is settling in Stokes' regime. So, Stokes' law is applicable. Under the Stokes' law, the settling velocity ut is equals to g dp square delta rho by 18 mu. So, there you substitute all the values g dp square rho p minus rho and then 18 mu, simplify, you will get settling velocity as 3 into 10 power minus 3 meter per second. So, but this transport also it was asked like at what mass rate per unit cross section area. So, that is G you have to find out. So, whatever the ut that you get from here, that you multiply by density of the fluid, that is 900 kg per meter cube, then you will get G as 2.7795 kg per meter square second. Okay. Now, we take another example problem, but the problem is quite similar, but here we use short cylindrical particles where d and h of the particle, cylindrical particle, are equal to each other, and then that value is 0.0127 meters. Density of the particle is given, fluidizing medium is air, density of air, viscosity of air are also given. The minimum fluidation velocity has to be found if the minimum fluidation voidage or voidage at minimum fluidation condition is 0.4. So, everything is known here, but only the particle is not a spherical particle. So, we have to find out sphere volume equivalent diameter dp, and then we have to find out pi s. Pi s we have already found in one of the previous chapter for a short cylinder as 0.847. That is pi s, the shape factor or sphericity does not depend on the size of the particle, it only depends on the shape of the particle. For short cylinders the sphericity is 0.847, that we have already done previously. So, we can use it. So, now sphere volume equivalent diameter dp you can find out by 6 Vp by pi s Sp. So, 6 by pi s is 0.847, Vp is nothing but pi d square by 4 into h. Now, h is also equals to d, and then Sp is 2 pi r square, that is 2 pi d square by 4 plus pi d, h is now d anyway. So, pi d d. So, h is equals to d. So, that you substitute here. So, when you do simplification, because now everything is known here. So, this what you get here, from here you get dp is equals to d by 0.847. So, that is 0.0127 by 0.847, that is approximately coming out as 0.015 meters. So, this value you have to use in the corresponding equation for a minimum fluidation. So, minimum fluidation equation is this one, that is we have been using the same equation. So, here also we have to use the same equation, G rho p rho mu epsilon m dp pi s, everything is known here also in this equation also. So, except the VO m bar, everything is known. So, you substitute and then simplify, you obtain the solution for this equation. So, you get minimum fluidation velocity as 3.084 meter per second, quite high minimum fluidation velocity compared to the other previous example problems. Okay, one more example problem. Here what we do, minimum fluidation velocity, if it is known, we have to find out the voidage at minimum fluidation condition. So, that is what we have to find. Okay. So, consider a column of diameter 0.61 meter and height of 2.44 meter is packed with spherical particles of diameter 12.7 mm and particle density 1500 kg per meter cube. Air flows through the bed at a rate of 0.358 kg per second. Okay. So, the velocity flow rate is not given in a kind of in terms of velocity, but it is given as mass rate in kg per second, and it incurred minimum fluidation when the air is flowing at this mass rate. So, that is providing minimum fluidation. So, this mass rate is corresponding to the minimum fluidation velocity. Okay. The density and viscosity of air are given. So, calculate the voidage of the bed at minimum fluidation conditions. Okay. So, we need to find out what is G, because here in the problem the VO m bar is not given directly, right. So, in the equation we cannot use directly. So, what we do, that equation minimum fluidation velocity or equation corresponding to minimum fluidation, that we write in terms of G, and then G we can find out from here by dividing this mass rate by the cross section area of the column. So, first we have to find out cross section area of the bed, that is pi d square by 4, that comes out to be 0.2922 meter square. Then mass velocity G, that is corresponding mass velocity is corresponding to the minimum fluidation, it is given in statement. So, rho VO bar should be rho VO m bar, because at this corresponding to at this mass flow rate the minimum fluidation has occurred. So, we have to take rho VO m bar. So, air flow rate divided by the cross sectional area. So, rho VO m bar or G we get as 1.1225 kg per meter square second. So, at minimum fluidation condition we have this equation. Now, again here we right hand side we multiply and divide by the density, so that we have a kind of a rho VO m bar terms, those terms we can replace by G. So, that this equation would be in terms of G, or G is already we have calculated. So, in this equation everything is known, this is nothing but G, this is nothing but G square. So, G we have already calculated as 1.1225, and rest all the properties are also known here, okay, except the voidage at minimum fluidation condition. Except epsilon m, everything is known. So, if you substitute all the numbers, you get an equation for epsilon m like this here. This equation if you solve, you will get epsilon m closely 0.219. Okay. So, voidage at minimum fluidation condition is 0.219 for this condition. So, the same equation, different problems we have taken, different way, different quantities we can calculate using this equation. So, this is about the minimum fluidation and then corresponding problems on minimum fluidation. Now, we go to the next part of the lecture, that is other types of fluidation, what we can get. So, expansion of fluidized beds. So, the superficial velocity when it is increasing, whether it is a gas or liquid fluidizing medium, the bed is expanding, the bed height is expanding, that is what we have seen, right. So, now how much is increasing the bed height, or how much expansion is taking place, that we have to find out, or when the minimum fluidation velocity, beyond the minimum fluidation velocity, if you increase the superficial velocity, the due to the expansion bed voidage is also increasing, how much that is increasing. So, that epsilon at expanded conditions, or height of the expanded bed, that is L or epsilon, we have to find out for the expanded bed. For expanded bed, velocity is much more higher than the minimum fluidation velocity. Okay. So, now what is that? Here the velocity is not a kind of independent variable, it is input condition dependent variable, right. Okay. Independent variable is either L bed height or voidage of the bed at expanded conditions. So, those things we are going to find out for different types of beds, okay, or different types of fluidation, especially for expanded fluidized beds, and then particulate fluidation, and then bubbling fluidation. For 3 cases we are going to do this one. Expansion of fluidized bed, that we have seen irrespective of the fluidizing medium, whether gas or liquid is the fluidizing medium, that is for both gas solid system and then liquid solid system, the bed expands as the superficial velocity increases, and then once the fluidation, minimum fluidation has occurred. So, as you increase the superficial velocity, pressure drop remains constant, it does not change with the superficial velocity, but the pressure gradient decreases as the epsilon m or as the epsilon increases. Okay. So, pressure gradient decreases as voidage increases, right, because initially the voidage is low, but now the velocity is increased, superficial velocity is increased beyond the minimum fluidized conditions, right. So, that is the reason the voidage is increasing, bed expansion is taking place, particle volume is remaining same. So, when the bed expansion is taking place, overall volume of the bed is increasing. So, but the particle volume is same, corresponding the voidage volume will increase. So, that means epsilon will increase. So, when epsilon increasing, though the pressure drop is remaining constant, but the pressure gradient is decreasing according to this equation. That is what we have been using. Okay. So, this is the equation one can solve and then get the details of the voidage, etc. That depends on the how much is the expansion. Okay. So, let us say now particulate fluidation. Particulate fluidation, we just recapture here a kind of uniform expansion of the bed is taking place, right. So, particulate fluidation, first of all it occurs when the fluidizing medium is a kind of liquid, and then across the cross sections the bed is so uniformly expanding that across the different cross sections or different locations in the bed, if you try to measure the bed density, it is going to be almost constant. Okay, that is what we have seen. So, now what we see, so if this expansion pictorially it shows like it is almost like very entire column has been particles are reaching almost to the top of the column, but assume this let us say if you assume this corresponding to initial packing height, right, the expansion is only small, it is uniform, but it is expansion is only small. Initial bed height was this one, but now it is expanded, slightly expansion, we are not taking that expansion is taking so much. Why? Because we are making some kind of simplification so that we can use the existing equation to find out what is this expansion, how much it is expanded or how much it is voidage has increased because of the expansion, that we can calculate. Okay. So, the bed is so uniformly expanding that is almost like a kind of packed bed structure only it is there. There is no abnormality across the different levels in the bed as you move up from bottom to top or top to bottom. At any location the uniformity of the bed is there almost. So, what we can say, whatever the Ergun's equation is there, that can also be used even for the particulate fluidation, provided the expansion is only slight expansion, it is not large expansion, that is only slightly expanded beyond the minimum fluidation condition. Then we can use the Ergun equation also here. Okay. So, if we do that one, what we get? Here what we can see, expansion is uniform. So, Ergun equation is expected to hold approximately well for slightly expanded bed, not very largely expanded. Particulate fluidation, but only slightly expansion we are considering. Under those conditions only this equation, whatever Ergun equation we are going to use to get the things will be valid. Okay. So, then for laminar flow conditions, the first term of Ergun equation leads to the following form for the expanded bed. So, this is the Ergun equation. Okay. So, this Ergun equation, the first, this is the Ergun equation here. Okay. Now, in place of delta p by L, if you replace G into 1 minus epsilon rho p minus rho p, then that will be corresponding to the expanded bed conditions, right. So, now if you equate this particular part, right. So, if you equate these two terms, what you will get? You will get an expression for epsilon. So, you can write epsilon cube by 1 minus epsilon as 150 V O bar mu by G rho p minus rho pi s square dp square. So, remember here this equation here exactly same as a kind of equation for a minimum fluidization velocity, but when you use the same equation, this equality whatever we have done here. So, when you use it here for the calculation of minimum fluidization velocity, there epsilon m or the voidage at minimum fluidization velocity is known. It was not independent variable, it was dependent variable and known variable, input variable, that is what we have seen. And then superficial velocity corresponding to minimum fluidization, that is the VOM bar was independent variable. So, we used this equation to get the VOM bar from here. Now, in this condition, expanded bed condition, the superficial velocity is beyond the minimum fluidization velocity, but the expansion is very small. Expansion is very slight. So, then we are using the same equation. Here we are trying to find out what is the voidage, right, because now the velocity is known, it is beyond the superficial velocity, some known velocity you are giving. Okay. So, corresponding epsilon we have to find out, that is the unknown now. Okay. L and epsilon are unknown. Okay. So, this is what we can see here. So, now you can see this equation number 2 and then this equation for minimum fluidization velocity, they are similar to each other indeed, right. Okay. So, but only thing that here in the minimum fluidization velocity is independent variable, whereas in the present case VO bar is a kind of independent variable and then epsilon is a kind of dependent variable, whereas in the minimum fluidization condition this VOM bar is dependent variable and epsilon m is known and independent variable, that is the difference. So, the same equation we are using here to calculate the minimum fluidization velocity, same equation here we are using to get the voidage for the expanded bed which is beyond the minimum fluidization condition. So, superficial velocity is known. So, that means epsilon cube by 1 minus epsilon is proportional to the superficial velocity, provided the superficial velocity is greater than minimum fluidization velocity. Okay. If VO bar is equals to minimum fluidization velocity, then epsilon is nothing but epsilon m. So, now bed height if you wanted to calculate for the expanded bed, then we have two equations, indeed one equations only. So, under the expanded bed conditions, delta p by L we can write G 1 minus epsilon rho p minus rho, but now L suffix E epsilon suffix E I am writing just to indicate this is for the expanded conditions, but the same equation is valid under the for the minimum fluidization condition, or from the minimum fluidization point onwards, whatever the velocity you increase, whatever the bed expansion takes place, the pressure drop is remain constant, okay, and then pressure gradient is equals to G into 1 minus epsilon rho p minus rho. So, under same equation under two conditions we are using. So, now this is here epsilon m, Lm we are using because these equations are now under minimum fluidized bed conditions, right. The equation exactly same, but one is at the expanded condition, another one is the minimum fluidized condition. Expanded conditions are beyond the minimum fluidization condition, so that the enough expansion is taking place, but that expansion is not too high, so that Ergun equation can be used. So, from these two equations what we can write, Le is equals to Lm multiplied by 1 minus epsilon m divided by 1 minus epsilon E. So, that means from this equation if you wanted to find out the height of the bed expansion, how much expansion of the bed has been taken, if you wanted to know, you should know what is the voidage of the bed at that expanded conditions. or the voidage of that expanded bed, that you should know, otherwise you cannot use. Okay? Otherwise this equation is not good enough to use. So, what we do here, there are some kind of empirical correlations based on the experimental studies are there between superficial velocity and then voidage for expanded bed conditions. So, for expanded bed conditions, superficial velocity is equals to voidage of expanded bed power m. This m is a constant which depends on the particle Reynolds number, right. It depends on the particle Reynolds number, not the Reynolds number for the packed bed. It depends only particle Reynolds number. It is similar like we have N versus REP for the hindered settling case, right. Similarly, M versus REP is available for the expanded beds also. Similar like that. If you remember that hindered settling conditions, there also suspension velocity US is equals to ut, that is free settling velocity of single particle multiplied by epsilon power n, and that n was depending on the particle Reynolds number. Similarly, here also for packed bed or expanded fluidized beds, there is a relation between the superficial velocity and then a voidage, and then this power m is dependent on the particle Reynolds number. So, if you know the Reynolds number, dp VO bar rho by mu, this is for the particle, because we are not dividing by 1 minus epsilon, right. If you know this thing from this graph, you can know m. So, once m is known, then you can calculate the required things. Okay. So, how to calculate, we see an example here. So, bed of spherical beads diameter 1.1 mm having density rho p is equals to 1240 kg per meter cube. Fluidizing medium is water with density and viscosity, so 1000 kg per meter cube and 0.01 poise respectively. So, what is the minimum fluidation velocity with epsilon m is equals to 0.4. Indeed, up to this part we have already calculated in one of the example problems, but here again we need to calculate because that is required for the next part of the problem. Next part of the problem is what is the superficial velocity if you want to have 25% expanded bed. So, initial bed whatever there, let us say initial bed is, let us say some like 1 meter. So, then if you wanted to have 1.25 meters of the bed height, so how much superficial velocity should you provide, and then corresponding voidage is what, that is what you have to find out. So, minimum fluidation velocity, this is the equation, we have done several problems, right. Here everything is known except the minimum fluidation velocity VO m bar. Now, here in this equation you substitute all the terms and then simplify. Okay. I have done this one in CGS units. Okay. So, then you will get VO m bar as 0.194 centimeter per second. Okay. So, now second part, superficial velocity at 25% expanded bed calculation. So, we have this equation for VO bar for expanded beds, but we do not know what is epsilon E. If we know that one, we can calculate it. Okay. So, and then we do not know m also. So, we have to calculate both. M we can calculate from the graph m versus REP. So, first let us calculate REP. REP, if we calculate substituting all the values again in CGS units, you will get REP as 2.646, and then from the graph for the corresponding REP is equals to 2.646, what is the m value, that is you can read out from the graph as 3.9. So, this equation under two conditions if you apply for VO bar and then VO m bar. So, then what will have, you will be having epsilon E by epsilon m power n, because this condition is valid from the minimum fluidation condition onwards till the expanded bed, right. So, that is what this equation we can have, epsilon E by epsilon m power 3.9 is equals to VO bar by VO m bar. M is 3.9, that is we know it actually. Why we are writing it here? Because VO bar is nothing but epsilon E power 3.9 E, but how to find out epsilon E? For that we may be needing this expression. Okay. So, at 25% expansion, that means LE is equals to 1.25 LM. So, after minimum fluidation 1.25% it has expanded. So, 1.25 times the height at the minimum fluidation conditions. That is what you mean by the statement. Okay. So, then from here LE by LM you can write it out, this equation already we have got it, previously derived it. So, here in this equation for LE by LM you substitute 1.25. So, 1 minus epsilon m by 1 minus epsilon E is 1.25. From here 1 minus epsilon E you will get 0.48, that means epsilon E is 0.52. So, now this equation epsilon E is also known. So, you can find out what is this one. So, when you substitute this one you will get VO bar as 5.40 mm per second. 5.40 mm per second you will get superficial velocity. That is, when you maintain a superficial velocity of 5.4 mm per second, then the bed expansion 25% expansion of the bed will take place. Now, bubbling fluidization. So, let us see the picture again. What happened? So, this is the initial fixed bed conditions. Okay, our initial height of the bed, it is like this. Okay. So, now when the superficial velocity or the fluidizing medium, when you use gas and then superficial velocity you increase beyond the minimum fluidization velocity. So, bubbling fluidization is taking place here. So, now you can see most of the bed is these voids are forming or bubbles are forming and they are raising up. Okay, they are raising up. So, most of the expansion of the bed here, what we can see, that is because of the expansion of the bubbles, whereas the particles are more or less they are remaining, if not exactly initial position. So, they are more or less corresponding to the bed height at the minimum fluidization condition whatever were there, up to that one only they are mostly expanding. Beyond that is more or less gas is only expanding. Of course, there are a few particles, but there are very few. So, what does we can say, even under the bubbling fluidizing conditions, particle phase or dense phase is at minimum fluidization velocity conditions only, and then bubble phase or bubbles are at certain average bubble velocity UB. So, whatever the bubble fraction, if you know, or the volume fraction of the bubble if you know, so what you can write, the total superficial velocity you can write it as bubble fraction multiplied by the average velocity of the bubble fraction. So, what is the remaining fraction other than the bubble is there, that would be the particle fraction or the dense fraction. So, that would be 1 minus FB, and that dense phase is at minimum fluidization velocity conditions. Okay. Similarly, L, whatever the bed is there, so LB bed expansion. Now, B I am using because in order to distinguish in terms of the bubbling fluidization. So, that would be 1 minus FB only. 1 minus FB is the particulate phase, and that phase is high, rising almost to the height of the bed at minimum fluidization conditions, isn't it? So, that means Lm is equals to Lb into 1 minus Fb. So, these are the approximation we are using. Approximation, but reliable approximation you can see from these pictures anyway. So, the bubbling fluidization where most of the bed expansion is taking place because of the expansion of the voids or bubbles are forming, whereas the dense phase is almost like expanding as a kind of minimum fluidization conditions only. Okay. So, under those assumptions we try to develop equations here. So, this is the assumption that we are having. So, then we get this equation as I already described. Okay. So, here now how to find out this minimum fluidization, the bed height corresponding to the expansion, what is the expansion height and then what is the corresponding voidage, those things we are going to calculate for this bubbling fluidization condition as well. So, here as I mentioned, Fb is the fraction of bed occupied by the bubbles or bubble volume fraction, then Ub is the average bubble velocity. So, this equation if you wanted to know, this equation you should know Ub. What is the average bubble velocity? That is again very difficult to find out experimentally for each and every experiment. So, there are a few experimental studies have been done and there are empirical correlations are available that we will see anyway. So, bed expansion also we can see the height of the expanded bed times the fraction of dense phase must equal to the bed height at the incipient fluidization condition, as I explained using the figure just now. Okay. So, these equations when you combine together, from equation 5 we are having this equation. Okay. So, you expand this equation so that you can write FB is equals to V naught bar minus VO m bar divided by UB minus VO m bar. From here 1 minus FB you get this thing. Why are we writing 1 minus FB? Because if you wanted to know height of the expanded bed under bubbling fluidization condition, that LE, if you wanted to know, you should know 1 minus FB, because LM is equals to LE into 1 minus FB. So, there that equation 6, LM is equals to LB into 1 minus FB. Here LB by LM you can write it as UB minus VO m bar divided by UB minus VO bar, and then this UB you need to know. You need to know, as I mentioned, from experimental studies, each and every experimental studies finding them is very difficult. So, already there are empirical correlations are available like this. UB is approximately 0.7 square root of G dB. G dB, dB is nothing but equivalent bubble radius, because in general these voids are forming, they do not form, the voids are bubbles which are raising through the packed area, they are not in a kind of spherical shape. In general they are in something like mushroom like shape or elliptical shape, like that only they are there in general. So, that is the reason equivalent spherical diameter of bubble is considered here. So, UB is known, so then you can use that equation number 7, previous equation, to get LE. Okay. So, this is about the bubbling fluidization. So, there are more other details are possible for each and every type of the fluidized bed. So, fluidization is a kind of very complex and turbulent, very complex behavior. Many times repeatability is also kind of a very different task. So, most studies one can be seen as a kind of separate course on fluidization. So, but at this course level this information is sufficient about the different types of fluidizations. Now, before concluding the fluidization part, we see some applications in terms of advantages and disadvantages also we will see of these fluidizations. Coming to the applications, fluid bed catalytic cracking in petroleum industry is the very famous one where the fluidization is used. Many catalytic processes such as synthesis of acrylonitrile etc., or many polymeric reactions or many gas phase reactions, SO2 conversion to SO3 etc., there also we use fluidized beds. Many solid gas reactions, fluid bed coal combustion is in general done in a kind of fluidized bed reactor, so that whatever the gases effluents carrying the energy are there, they will be collected and then they will be used for electricity production. Right. Fluidized bed coal combustion is also used as a mean of reducing boiler cost and decreasing pollutants emissions in general. For roasting of many mineral ores before processing to the subsequent unit processes, drying of many fine solids, adsorption of several gases also done in fluidized beds, and then there is a rigorous mixing of solids and fluids in general. So, because of that one there is no temperature gradient in the bed, even with quite exothermic or endothermic reactions in general. Rigorous motion of solids also gives high heat transfer rates to the wall or to the cooling tubes immersed in the bed in general. And then due to the fluidity of solids, these particles are easy to pass from one vessel to the other vessels. However, there are several disadvantages are also there with this fluidization. First of all, uneven contacting of gas and solid, especially in bubbling fluidization, as we have seen, our slugging fluidization etc., those we have seen there, we have seen there the contact is not even, as we have seen the contact is very even in a kind of particulate fluidization. So, for the gas solid system uneven contact is a kind of disadvantage, and then that is because generally gas passes through the bed as bubbles and directly contacts only small amount of solid in the thin shell known as the bubble clouds etc. As we have seen, these voids whatever the bubbles are forming, they are almost free of particles, and sometimes they are expanded so much that they are having contact with a less number of particles, and then small fraction of gas passes through the dense phase which contains nearly all the solids, unevenity, there is no evenity. Interchange of gas between bubbles and dense phase by diffusion and or by turbulent processes such as bubble splitting and coalescence occurs. Those things are again a kind of disadvantage. However, overall conversion of gaseous reactant is generally much less than the same that obtained using a kind of ideal plug flow reactor at a same temperature. Average bed density in turbulent fluidization is lower than in bubbling fluidization in general. However, in turbulent fluidization, mass transfer between gas and solids is much better compared to the bubbling fluidization, especially that is going to be useful in improving performance of chemical reactors. The finally very important one, the scale up of fluidized bed reactors is very uncertain, very uncertain, and an erosion of vessel internal parts and attrition of solids leading to loss of fines also occur sometimes in this kind of fluidized beds, which may be taken as a kind of disadvantages in several cases. References for this lecture are McCabe, Smith and Harriet, Ortega Rivas, Richardson and Harker, Giancopoulos, Brown et al., and then Badger and Banchero. But primarily most of the lecture is prepared from McCabe and Smith, and then some problems are taken from Richardson and Harker and then Giancopoulos. Thank you.